Hello, and welcome to this, the third video in my series developing the Arduino-FPGA shield. Now, in this video, I'm going to take you through the Jtag connectivity and then also the decoupling scheme for the FPGA. But before we do that, I just want to mention that all of the schematics from the previous videos have been uploaded to my repository on Git. You can access my Git repository either by coming to projects.hackaday.com, find the Arduino-FPGA shield project, and you'll find a link to my Git repository here. Or if you go to GitHub and you look up sfgit, that's SF as in San Francisco, GIT, you should find it there. Now, the schematics that I've published both in an Altium Designer format, which is the design tool that I'm using, but then also in a PDF format for those folks who don't have a copy of Altium Designer. If you take a look at the PDF inside Adobe Reader, you'll actually see that the hierarchy is also elaborated inside of the PDF document. I tend to use hierarchical schematics quite a bit, and the hierarchy will be represented there. You'll also get some nice bookmarking that makes it easy to do things like, for example, jump to components, and the reference designators for components will be bookmarked. Jump around to pins, nets, ports, all of that stuff. It shows up over here under the bookmarks. If you open this up in Chrome or something like that, you don't have access to the bookmarks. So unfortunately, you won't have the same navigation capabilities, but you will have all of the content there. So rest assured, you'll still be able to access the schematics and still use them. You just might have to do a little bit more bouncing around manually, scrolling up and down between sheets. I just like the bookmarks because it makes it easy to kind of jump around. Anyway, that said, so again, today we're going to talk about the Jtag configuration of the FPGA device and then decoupling. Now, a couple of things related to decoupling. I have uploaded also to my Hackaday project here the pin planning and layout guide. The decoupling scheme that we're using for this FPGA follows really to the letter the pin planning and layout guide, which is supplied by Xilinx. So the Xilinx guys will actually tell you specifically what sort of decoupling scheme you need to use for the package and type of FPGA device that you're using. So this one happens to be related to the Spartan 6, and we'll take a look at this a little bit later on. But inside this PDF document, they describe everything that you need to know about decoupling for the FPGA and give you specific instructions on what sort of decoupling capacitors to use. So it makes it very, very easy, once you know how to navigate the documentation, very, very easy to go ahead and implement an FPGA by yourself. So that said, let's go ahead and jump into my design tool here. Now, you'll notice first off that the schematics have changed quite a bit. They've grown. There's a lot of stuff on the schematics, where last time it was pretty sparse. The schematics themselves have actually grown. You'll also see that I've implemented some hierarchy here, which I mentioned a little bit earlier, but you'll see that I have sheets beneath sheets and that sort of thing. Part of the reason for the hierarchy, I feel it just makes things a lot more, or a lot easier to read. So, for example, here's the FPGA schematic. Below that, this symbol here represents my decoupling. That's a subsheet to this FPGA schematic. I think it makes it a lot easier to read, sort of grouping things in kind of a parent-child type relationship. Just a little bit more intuitive for me. You'll see that I've added quite a number of sheets also to the project. Rest assured, by the time we're done here, we'll go through all of the different aspects of this. At the very top of my design, I've created now a top-level schematic which includes a series of connectors, and basically this corresponds to the interface to my system, and this is just a convention that I tend to follow. So everywhere where I have an interface to the system or something like that, I represent that on the top-level schematic. That's the interface to the outside world. One layer down in my schematic hierarchy, I've got now sort of the internals of the system. So I've got the FPGA subsystem, which includes that FPGA schematic and the decoupling. I've got my SPI multiplexer, which we'll talk about in the follow-on video. And then we've also got the flash memory. So all of those different aspects, everything inside of the system, everything within the connectors that the system uses to interface to the outside world, I capture on a sheet labeled design. It's just a convention that I follow. And there's probably just as many conventions out there as you could care to know about, so take it or leave it, but it does make things a little bit easier for me. Now, also you'll notice that I've gone ahead and added a lot of these little bubbers onto the schematic here. These are groupings of signals that essentially what I've done is I've taken a series of signals, like for example my Jtag signals, which are down here, and I've grouped them together into a bus, which now I call hard Jtag. Okay, that includes all of the signals that I'm routing into this thing here. We call it a signal harness in Altium Designer speak. But basically, this label here, hard TCK, is wrapped up inside of this port, which if I jump from this port to the sheet that implements it, and then I go one layer up in the hierarchy, that then is broken out again and connects into my Jtag connector on that top level schematic. Okay, so you'll see a lot of that inside of my design. Just keep in mind that these labels, these are basically links to one another. Anywhere where you see two labels on the page, they will be connected together, whether I actually do explicit wiring between these things or not. Okay, so you'll see that used quite a bit in my design. Probably good for me to elaborate a bit on that convention, just so you know that, for example, the Jtag signals which exist here are connected to the Jtag signals which connect here, and then ported off the sheet. So, Jtag. Let's take a look at the Jtag connections for this part. But remember from the last video, the way that I've broken up this component, so the FPGA's got a lot of pins on it, and I've broken it up into subparts, not unlike the way that you would treat something like a quad op amp or something like that in a schematic. So this corresponds to U1A, this is U1B, U1C, D, this is E. On my decoupling schematic, I've got F and G. Sometimes these will even be broken across sheets like I've done here. Rest assured, all of these correspond to one part, which is component U1, and that's the FPGA, which is at the center of our Arduino FPGA shield. Now, going back into the FPGA schematic over here, U1E, I've gone ahead and grouped together the configuration pins of the FPGA device. Now, in this case, you'll recall from the previous video, we've got the done pin, the program pin, there's a suspend pin. We talk about those in video number 2, so I won't go ahead and go into detail on those. However, we've also got the Jtag configuration pins. Now, something to mention here. Whether or not you use SPI configuration or not for the FPGA, every one of the Xilinx Spartan 6 FPGAs has Jtag configuration capability. And that doesn't go away, regardless of whether you put something in master configuration mode or slave configuration mode or any of those things. Jtag configuration capability exists on the device, and it's always accessible to you. Okay, so this series of pins are dedicated pins for Jtag on the device, and they correspond to really two types of Jtag. So Jtag has the 1149 standard, which corresponds to boundary scan and really is intended more for debugging or getting access to specific what we call test access points, or areas inside of the device itself where I can read some data back from. And then you have the Jtag 1532 standard, which corresponds to in-system configuration, or ISC. So in-system configuration allows me to program the FPGA device. Now I'm programming the device directly. I'm not programming the SPI flash. Keep that in mind. So when I program this over Jtag, I'm actually programming the FPGA device. I'm not programming the SPI flash. So when the device reboots, it's going to boot from SPI flash. I'm not reprogramming the SPI flash. So just keep that in mind, because if you think that because you program the FPGA device, now the SPI flash is going to have that configuration, doesn't, okay? You need to program the SPI flash independently. Now, traditional boundary scan with Jtag, I'll give you an example of what that kind of looks like. If I bring this up over here, you'll see, and this is just kind of a nice view. Traditional boundary scan uses a series of test access points, or these points within the device itself, that sort of surround the device or go through the boundary regions of the device itself and allow me to read data back from the pins of the device through an interface into something called a tap controller. Okay, the tap controller basically just collects together all of the information about what's going on the pins and then sends that out through a serial bus that I access. That serial bus is ultimately that Jtag interface that I have there, interfacing to the tap controller. Now, the tap controller can also spin off and program the device itself. So in this case, I'm not going to go into a whole bunch of detail on that. My suggestion to you, though, would be that if you want to know a lot about the ins and outs of Jtag, watch David Jones' video on EEV blog related to Jtag. It's really good. But this data, which is coming back to me live right now from an FPGA, which I actually have running on a development board, this information here is actually true Jtag stuff. This is boundary scan, okay? And I'm accessing this via boundary scan, okay? Now, each device which I access over boundary scan has a BSDL file. The BSDL file, or the boundary scan device language, is a subset of VHDL, which describes the internal tap controller for the device itself. Okay, I'm not going to go into a huge amount of detail on that, but that would all sort of fall under Jtag 1149. In-system configuration is the 1532 standard. Okay, so don't get the two mixed up. One is largely used for debugging, where the other is used for device configuration. Both of them are Jtag, and both of them use the Jtag standard, but they are significantly different in terms of their net effect. So, in this case, I've got 4 Jtag pins: TDI, TDO, TMS, TCK. TDI is your test data input, TDO is your test data output. Now, I can run multiple devices in series with one another by connecting TDO from my Jtag programmer to TDI, and then that routes through the device, out through TDO, into TDI, out through TDO, into TDI, and so on and so forth, until I get back to TDI in the Jtag programmer, okay? Now, I also have TMS, which is my test mode select, and then my TCK, which corresponds to my clock. These two are always connected in parallel with one another, okay? So each device is connected in a parallel scheme to TMS and TCK. However, TDI, TDO, those are always connected in series. And you just have to remember that TDI has to always connect back into TDO, has to always connect back into TDI, such that by the time it gets back to the Jtag programmer, your TDO is looping through the device and coming back into TDI on the Jtag programmer, okay? Just very, very important. The internals of the device will actually route those signals that way, but you've got to have that loop in there. You've got to create that circuit. So, that said, where can I get a Jtag programmer to program my FPGA device? Well, if you take a look on the web, you can buy the sort of top shelf. Xilinx has what's called the platform USB cable. It's a $225 device, so it's pretty expensive. However, you can usually use a Jtag programmer to program more than one thing. Now, Xilinx uses their own software for programming FPGAs. It's called Impact, and Impact is part of Xilinx's Webpack. Now, the Webpack is their collection of software which you can download from Xilinx, and we'll use this later to actually develop the internals of the FPGA. So we'll write some VHDL code, we'll create some Verilog, we'll do some state machines, whatnot, and we'll program the FPGA. Impact is the programming component of that. So the programming cable uses Impact at the software side, so that's the software that you're running on your PC, to program the device via Jtag. Now, $225 is a little rich for my blood. If you search the web, you can find lower cost Jtag programmers. So, for example, there's a couple of $60 ones, a couple of $40 ones, $35 one. If you shop around well enough, you can definitely find a low-cost one. However, you need to make sure that it's compatible with the version of Xilinx Impact that you're going to use and the FPGA device that you're going to use as well. So, Jtag should be Jtag. Hey, it's a standard, right? But the software interface that you're using from the PC side to interface to whatever that device is needs to support the programmer that you're purchasing. So, if you're going to purchase a programmer that isn't the Xilinx platform USB cable or something like that because you want to do Jtag programming, let me encourage you to check first with the Xilinx Webpack software to see whether or not that programmer works with it, or check with an FAE or an AE or somebody from the someone from the company that you're going to buy the programmer from. Now, that said, let's go to the schematic for the design. Okay, so here are 4 Jtag signals. These are all going to be routed out to a header on the top level schematic, okay? We already saw that earlier. I'm taking these signals out and I'm routing them up to a header. As far as the wiring of this is concerned, it's really simple, okay? Generally speaking, the sort of accepted convention is to use a 10K pull-up resistor on each one of the Jtag lines. Look, the 4.7K pull-up resistor is absolutely appropriate for this, will totally work, and the nice thing about it is that it sort of fits with the standard that I use all the way across my design. So I tend to use as pull-ups 4.7K pull-up resistors, and I tend to use one pull-up resistor value, if I can, across the whole design. What does this do? Well, it helps to eliminate the need for me to go out and buy a whole bunch of resistors and have some 10K and some 4.7K and that sort of thing. Granted, I have them, but and they're cheap as chips. I can throw them away. However, I have gone ahead and tried to standardize on the 4.7K across the whole design just to make everything a little bit easier. So why do we use the pull-up resistors on Jtag? Well, the simple explanation is that we want Jtag to be in a known state at all times. So when I'm not doing any programming, when there's no connection into it, I want the Jtag interface to be in a known state with respect to the system. So that said, the pull-up resistors do exactly that. They ensure the fact that these are pulled up or pulled high, so the system is always in a known state. Now, I've also gone ahead and added some series terminations in here. And partly the reason I did that is I don't know how many Jtag devices I might have connected, but the series terminations help a little bit to ensure the fact that if I do have multiple devices connected along that Jtag bus, that I don't get any sort of weird signal anomalies or anything like that. So I've gone ahead and added 4 33 ohm series resistors also here as part of the connection into the Jtag pins on the FPGA device. So really, it's as simple as that. With that sort of wiring, and then broken out at the top level to the header that I'm going to connect into, what I'm going to end up doing is connecting a series of flying leads into this hard Jtag port here. Now, some of you may have noted rightly that I have a soft Jtag port on here. I'm not going to go into detail on that right now, but rest assured that is not a part of the normal Jtag standard. It follows the Jtag standard, but it's not part of the normal Jtag standard. I use that to do some debugging using a specialized piece of software, which is a part of Altium Designer, which allowed me to show you those the pin information and whatnot in the panel that I showed you earlier. So that said, it's not a hard, fast requirement to have these, but I am including those in this design specifically so I can play with this inside of Altium Designer. So that's it. Decoupling. Let's jump ahead now to the decoupling scheme for the FPGA. So if you recall, on my FPGA schematic now, I've created this subsheet. It's called FPGA Decoupling. And if I dive down into it, I've got a couple of different voltages coming into the sheet. Okay, I've got my auxiliary voltage, my internal voltage, which is going to be 1.2 volts. Everything else is 3.3, okay? My internal voltage here, though, is going to be 1.2 volts, and we'll come back to that later when I show you the power supply design, which will be in a following video. Now, I've got the decoupling scheme here, and if you recall from earlier, I mentioned that I have the component U1F and U1G. Both of these components now listed here, and those are essentially broken up. The way that I've done this is I've grouped the pins based on the I/O bank that each one of these power pins corresponds to. So each I/O bank on the device itself, and I've got 4 I/O banks here, are going to have a set of power pins which are appropriate for that I/O bank, which are going to provide power to that I/O bank. Okay. I've also got my auxiliary voltage over here and my internal voltage over here. So I've got those things grouped together. It just makes my schematic look nice. Now, I've also then broken these out. So this VCC-0 connects to VCC-0, connects to VCC-0, so these power objects all connect to one another over here. So where did I figure out where the decoupling comes from? Well, Xilinx, if you recall earlier, I mentioned there is this PCB design and pin planning guide. And again, if I jump back into my Hackaday project, I've added a link to that under my Hackaday project. That PCB design and pin planning guide, excuse me, let me go back to that, provides details under the section Power Distribution System for exactly what sort of decoupling you should use. And they do it on a device-by-device basis. So if I zoom in here, I've picked the Xilinx Spartan 6, we're using the LX9, and I've used the 144-pin TQFP package. So go ahead and try to highlight that again. this is the decoupling scheme that I'm going to use. This is the decoupling scheme that I'm going to use for that device. Now you'll see here, VCC int, this is my internal voltage. I'm going to use 3 4.7 microfarad caps, and then I'm going to use one 470 nanofarad cap, okay? Likewise, it's going to continue down the line here. Here's VCC aux, so my auxiliary voltage. Here's VCC O, so this is bank 0, bank 1, bank 2, bank 3. And it shows you exactly what capacitors you're supposed to use for that. So that said, super, super handy reference. All I've done on the schematic is go ahead and implement it following their rules. Now you could do some consolidation. Again, if you have space constraints, if you have board area constraints, something like that, you could do some consolidation, you could do some tweaks, you could play with the decoupling scheme a little bit. Experience will point you in the direction of what you could do. However, if you want to be right 90% of the time or 95% of the time, follow the instructions that the Xilinx guys give you. It's very, very good information. Likewise, they also give you information on basic things like PCB materials, the traces that you're supposed to use, high-speed signaling, I/O and clock planning, that sort of thing. Really, really good information in this guide. So let me encourage you that if there's anything that you feel is left to chance, jump around and take a look at the documentation, because it definitely is an RTFM world with respect to the FPGA vendors. They do a great job of providing resources. So, that said, that's kind of where we're at. Now, if I dive back into the schematic over there, this gives us the decoupling. We've got the Jtag interface nailed, okay? The next things that we're going to look at, which are going to be in the following video, are just basically what I/O banks we want to break out, and what I/O pins, or how many I/O pins we want to break out from the I/O that we have left over, and there's a lot of I/O left over. We'll also go ahead and take a look at the power for the design itself, and I'm not completely done with that, so I'm not going to show you this design quite yet. But we'll take a look at the power supply for the FPGA design, because remember, we're going to power this both from the Arduino, but I want this to be functional as a standalone system. So we'll also look at using a power connector and a proper power connector, so this thing can be plugged in and programmed using a Jtag connector and a regular old wall wart that you might plug into the board itself. So you won't require the Arduino to power the board itself, okay? And then also, we're going to go ahead and take a look at the interface to the Arduino connectors, and how many of the pins will interface to the Arduino connectors and that sort of thing in that scheme. It's still kind of up in the air. I haven't decided 100%, but if anybody has any input, please leave it in the comments, or please go ahead and leave it in the comments on the Hackaday page. And if you like the project, if you like the videos, by all means, come over to Projects on Hackaday and skull me. What that means is give me a skull, and my project will show up towards the top of the list, and we'll hopefully gather a little bit more interest. Also, we should close on this by the end of the week. When that happens, I will be going out to build some prototypes. If anybody's interested in a prototype, by all means, drop me a line in the comments or something like that, and I'll be more than happy to shoot you a board at cost, whatever my cost is on it. Again, my target is to try to keep this under 30 bucks. I've already ordered components. That looks pretty likely. So that said, I hope you enjoyed this, and if you have any questions, comments, feedback, anything, go ahead and let me know. Thanks.